So continuing on from the last lesson, quantized energy and photons. So as it turns out, when we analyze light, it turns out this just doesn't have just wave-like properties. It turns out it also has particle-like properties. And when we analyze three different phenomena not explained by the wave nature light, one being blackbody radiation, another one being photoelectric effect, and the last one being emission spectra, all three of these give us an idea that maybe waves or light in particular don't just have wave-like properties, they actually have particle-like properties. And so with blackbody radiation, that's just light coming from a heated object. So whenever we talk about blackbody radiation, anytime you heat metal, if you get it really hot, it can start turning red. That red color that comes out of the metal, that's basically called a blackbody radiation. The heat that comes out, that red, photons are being released as you heat this object. And the higher the temperature of the object, typically the further along on the right of the color spectrum you get. You go from red to orange hot, to yellow hot, to green hot, to blue hot. And when you get to white hot, that means you have all of the colors now combined. So you're getting black, red, and that's what white light really is. It's actually all the colors combined. The photoelectric effect, on the other hand, is where electrons are emitted from light illuminating surface. So if you take an X-ray and shoot it on a piece of metal, you'll wind up tossing electrons off of that piece of metal as the photons bounce off of it. And emission spectra, this is light from electronically excited gas atoms. So whenever you look at the light above in these fluorescent light bulbs, we're basically dealing with emission spectra. And we'll talk about how these are all different. So let's talk about blackbody radiation. Blackbody radiation, as I said, is when you have hot bodies emitting radiation. As seen in a red glow of an electric heater or the bright light of a tungsten light bulb. So those light bulbs that you have at home that have those little, the light bulbs that look like this, so a light bulb that looks like this, that you plug into your normal, with the spiral here. Inside there's a filament. And that filament, when you heat it up, will then create light. And so the idea is that the glow from that is actually due to tungsten being heated at a high temperature because of friction of the electrons occurring in there as they all try to pass through that small little wire. It winds up heating up and you create light that way. So the color or wavelength of light depends on the temperature. Red hot objects are cooler than white hot objects, as I said a second ago. And scientists struggled to understand the relationship between temperature, intensity, and wavelength of an emitted radiation. And so with that struggle, of course, given that light seemed to have wave-like properties, they didn't understand how all of that worked together. Max Planck in 1900 named each small chunk of energy emitted a quantum, meaning a fixed amount. And so conceptually speaking, it turns out that the energy that light is emitted or absorbed are emitted or absorbed in discrete units or quantum packets of energy. And so it's not just one big packet of energy from like a wave, like in an earthquake. We're talking, small chunks of energy that are actually high energy. Planck proposed that energy of a single quantum equals a constant times its frequency, hence the formula we learned in class today. E equals h times the frequency. And E, of course, has to be in joules. H is Planck's constant. In class, I used 6.626. Although this one says 6.63, it's a little bit rounded. I like 6.626 better. And V, of course, or nu, is the frequency in hertz. And so if I want to calculate the energy, all I need to know is the frequency, and I can actually figure out, by multiplying frequency and Planck's constant, the energy of the radiation. Although small, quanta are significant amounts of energy on the atomic level. So just keep that in mind. I know it looks like they're small numbers because it's times 10 to the minus 34 joule seconds here, but they are significant at the quantum level. So according to Planck's theory, energy is emitted or absorbed by matter of whole number multiples of hv, in whole number multiples such as hv, 2 times hv, 3 times hv. And an analogy in terms of what they always talk about when they talk about energy is that instead of a continuous ramp where you have continuous energy along this ramp, a staircase has very specific steps of energy. And so when we talk about blackbody radiation, we think about the steps of energy that it actually has. So what is the photoelectric effect? Well, this one's actually discovered by Einstein, and the idea is that when light shined on a clean metal surface, it causes electrons to be emitted by the surface. Each metal has a different threshold below which no electrons are emitted. And this is actually a topic they study significantly in physics. It's not a topic we cover in chemistry in great detail, but it reveals a little bit about the nature of light that helps us understand how then electrons are structured inside. And so when you have an incoming photon hit the surface, you wind up having an outgoing electron that comes right out of this whole, you have an electron that shoots out as a consequence as this photon gives that electron energy. And so light must be in little chunks called photons for this to happen. And radiation is quantized, and of course that's again verified by Einstein. So then the question is, why are X-rays powerful enough to cause cancer? Well, it's because it has the ability to remove electrons from your DNA. And if you remove electrons from your DNA, you wind up changing its chemical structure. And if you change the chemical structure, as I said in class, you wind up having issues of mutations. And mutations that create proteins that are not safe for your body are the cancers. And of course, he solved this back in 1905. Light, basically, he said, has both wave nature and particle nature. Particle nature because it has the ability to remove an electron. And if it was a wave, it wouldn't have that ability. And because it is a particle, it's able to then remove another particle from its system, that being an electron inside a metal. Photon is a particle of light, and it has both frequency and particle nature. So it's interesting. It's an interesting duality in physics. It again just reveals a little bit about the structure of the electron, which we're going to be studying here in a second. And of course there's a formula for this. Again, this formula is something we don't use. This is something they use in physics, so don't worry about copying this down. Just understand that through this experiment we know that light has both wave nature and particle nature. So as an example, so take a pause and try to practice this problem. When copper is bombarded with high energy electrons, X-rays are emitted. Calculate the energy in joules associated with the photons if the wavelength of the X-rays is 0.154 nanometers. So of course the issue here is they give me wavelength. And so with wavelength being given, I can't use it directly into the formula E equals h times nu, which means I have to manipulate the formula. And so to manipulate the formula, we use the second formula, which is, and so let me write that down over here. So E equals h times, equals h times nu. We said that C equals lambda times nu, and I can solve for nu by doing C divided by lambda. Plugging that in there, you get E equals hc over lambda. And that's how they get that formula on the left-hand side over here. And when you plug that in, that means I just need Planck's constant, I need the speed of light, and I need the wavelength. Luckily, I have the wavelength. The problem is it's in nanometers, so I got to convert that guy. Well, the easiest way to convert it is if you know that 1 nanometer is equal to 10 to the minus 9 meters. So instead of writing nano, I write 10 to the minus 9 into my problem. So when I divide this, and again you have to be very careful when you divide this has to be in parentheses when you divide. 6.626 times 10 to the minus 34 times 3 times 10 to the 8 divided by this number right here, all together, you wind up getting an answer of, units of course cancel out, and of course it's not even showing my seconds canceling very well, and my meters canceling. I wind up getting joules, 1.29 times 10 to the minus 15 joules. So that would be the energy associated with a one single X-ray. So it doesn't look like a lot of energy, but for one single X-ray, that is very dangerous. So, so is light a wave or a particle? Macroscopically, it behaves like a wave, but on the atomic level, we observe particle properties. So where am I? Or what is my momentum? Or where am I? Oh hell, why worry about all that again? I'm not even sure I'm a wave or a particle. So that's just a little cartoon on photon self-identity problems, because it doesn't know if it's a particle or a wave. Kind of a stupid joke, I know. You don't get it. And that's it for now. Next thing we're going to do is we'll talk about how all of this then how it helps us understand the internal structure of the atom.